If you could drain a slice of the North Atlantic and stand on the seafloor, you'd be staring at something that makes the Grand Canyon look modest. Imagine a canyon wider than 80 kilometers, deeper than 4 kilometers, stretching for hundreds of kilometers across the ocean floor. Now imagine this. It wasn't carved by a river over millions of years. It was torn open by plate tectonics. Hidden about 300 kilometers east of the Mid-Atlantic Ridge lies the vast submarine rift system known as the King's Trough. It doesn't have tourist outlooks or Instagram sunsets. It doesn't have rafters floating down a muddy river. What it has instead is raw tectonic violence frozen in time. A scar in the ocean crust that records a brief moment when continents shifted, plates reorganized, and a mantle plume was stirring beneath the Atlantic. To understand how it formed, we need to rewind to a time when the Atlantic Ocean was still evolving into its modern shape. The oceanic crust beneath King's Trough is between roughly 60 and 26 million years old. That crust formed at the Mid-Atlantic Ridge, the long volcanic seam where North America drifts away from Europe and Africa. At a mid-ocean ridge, molten rock rises from the mantle, cools and becomes new seafloor. If you picture the Earth slowly unzipping itself down the middle of the Atlantic, that's essentially what's happening there. But something unusual was happening around 45 degrees north. The crust in this region isn't normal thickness, it's thicker, more buoyant, and chemically enriched. That enrichment points to a mantle plume, a column of unusually hot rock rising from deep within the Earth. A mantle plume is like the thermal updraft in a mantle, similar to a hot air balloon rising through the atmosphere. It brings extra heat and material upward, increasing melting. Today, the Azores sit above such a plume, but evidence suggests that millions of years ago, an early branch of that plume was interacting strongly with the Mid-Atlantic Ridge near 45 degrees north. When a mantle plume and a spreading ridge interact, you get more melting than usual. More melting means thicker oceanic crust, and that thicker crust built a broad, underwater plateau in the region. So before King's Trough ever formed, this part of the Atlantic was already special, hotter, thicker, more buoyant than average. Then, around 37 million years ago, the tectonic choreography changed. The boundary between the Eurasian plate and the African/Iberian plates jumped northward into this area. A plate boundary is where two massive slabs of Earth's lithosphere, the rigid outer shell of the planet, interact. Most of the time in the Atlantic, plate motion is simple. Plates move apart at the Mid-Atlantic Ridge, but occasionally boundaries reorganize, they relocate, they experiment. Instead of forming a new spreading ridge, this new boundary manifested as oblique extension and right-lateral motion. In simpler terms, the crust was being pulled apart and slid sideways at the same time. Geologists call this transtension. Transtension is what happens when stretching and sideways sliding combine, creating elongated basins and fault systems. The result was King's Trough. Rather than being carved by erosion like the Grand Canyon, it formed as a graben. A graben is a block of crust that drops down between two faults during extension. If you pull a chocolate bar apart and the center cracks and sinks slightly, that sunken section is analogous to a graben. The flanking ridges of King's Trough are essentially the uplifted shoulders of that drop block. Magnetic anomalies on the seafloor, patterns formed as lava cools and records Earth's magnetic field, show the trough open progressively from east to west. The offsets increase toward the eastern end, meaning the rifting initiated there and propagated westward. It's like tearing a sheet of paper from one edge. The rip travels along the sheet. The deepest parts of the complex, the Peake and Freen Deeps, reach nearly 6 kilometers below sea level. These are even deeper than the main trough and are geochemically distinct. Their volcanic rocks resemble normal mid-ocean ridge basalt, rather than plume-enriched material. That tells us something fascinating. The most extreme stretching occurred outside the thickened plume plateau, where the crust was more normal and easier to thin. Thickened crust, like that produced by plume interaction, can actually resist extension to some degree. It's hotter and more buoyant. In contrast, cooler and thinner crust nearby was more susceptible to deep rifting, so the biggest collapse zones formed just beyond the plume-thickened area. This rifting phase lasted from roughly 37 million years ago until around 20 to 23 million years ago. Then, just as abruptly as it began, it stopped. The plate boundary relocated again, this time southward, to what is now the Azores-Gibraltar fracture zone. When that happened, extension at King's Trough shut down. The mantle plume's focus shifted southward as well, contributing to the development of the modern Azores Plateau. King's Trough was effectively abandoned. That's one of the most intriguing aspects of this structure. It represents a failed plate boundary, an experiment in tectonics that lasted perhaps 15 to 20 million years before being superseded. Oceanic lithosphere doesn't often preserve such clear evidence of transient plate reorganizations. Usually spreading ridges and transformed faults dominate the picture, but here we have a short-lived intraoceanic rift frozen in place, and the scale is staggering. The Grand Canyon is about 446 kilometers long, up to 29 kilometers wide, and about 1.8 kilometers deep. King's Trough is shorter in length at roughly 350 kilometers, but it's up to 80 kilometers wide and more than twice as deep. If you drained the Atlantic in that region, you would see walls rising kilometers above the vast basin floor, a canyon system of tectonic origin rather than erosional artistry. There's another key difference. The Grand Canyon records erosion through sedimentary rock, layer upon layer telling a story of ancient deserts, shallow seas, and river systems. King's Trough records internal earth processes, mantle melting, plume ridge interaction, lithospheric stretching, and plate boundary migration. The volcanic rocks dredged from the trough flanks are mostly alkaline basalts with ocean island basalt characteristics. Ocean island basalt, or OIB, refers to lava derived from mantle plumes rather than typical ridge melting. In simple terms, their chemistry tells us that they came from a deeper, hotter, and slightly different mantle source compared to normal mid-ocean ridge basalts. Radiogenic isotope data, ratios of elements like strontium, neodymium, hafnium, and lead link these rocks to the same mantle reservoir feeding the Azores. Isotopes are essentially atomic fingerprints. They allow geologists to trace magma back to its mantle source. In this case, the isotopic fingerprints match those of the Azores plume. So King's Trough isn't just a canyon. It's evidence that the Azores plume was once interacting strongly with the mid-Atlantic ridge at a more northerly latitude than today. It also tells us something subtle but profound about how the lithosphere behaves. Thickened plume-modified crust does not simply respond passively to tectonic forces. It influences where rifting localizes, how deep basins form, and how magmatism is distributed. The trough's flanking ridges may represent tilted graben shoulders, blocks uplifted as the central region subsided. In some places, volcanic edifices like seamounts formed later, around 10 to 11 million years ago, showing that plume influence persisted even after major rifting ceased. When you step back and take a look at the broader picture, King's Trough sits at the intersection of three powerful forces: a mantle plume rising from deep within the Earth, a spreading ridge generating new oceanic crust, and a migrating plate boundary briefly trying to establish itself. That three-way interaction is rare. Most geological features are products of one dominant process: erosion, volcanism, or tectonic compression. King's Trough is a hybrid. It is a tectonic canyon formed in plume-thickened oceanic crust during a transient phase of plate reorganization in the North Atlantic. And unlike the Grand Canyon, which continues to evolve as the Colorado River cuts deeper, King's Trough is essentially static. It's a fossil structure on the seafloor. Sediments have smoothed its floor. The plates have moved on. The plume has shifted south. The tectonic drama ended millions of years ago, but the scar remains. If you could stand on its edge, 4 kilometers above the basin floor, you would not see layered sandstone cliffs glowing in sunset light. You would see basalt walls formed from molten rock, faulted and tilted, descending into darkness. No river carved it, no wind shaped it. It was ripped open as continents adjusted their positions on a restless planet. In many ways, that makes it even more impressive, because while rivers are powerful, plate tectonics operates on an entirely different scale. It reshapes ocean basins. It reorganizes continents. It lifts mountain ranges and opens seas. King's Trough is a demonstration that some of the most dramatic landscapes on Earth are invisible beneath the waves, not carved from above, but torn apart from below. I hope you found this as interesting as I did, and as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.